Okay, the reason why factorials is combined is that factorials are very similar. They're actually just a shortcut for solving a lot of these fundamental counting principle kind of questions. So in the first question here, you've got A, B, and C as 3 children. So they don't have names, just letters assigned to them, A, B, and C. How many ways could you order them? So making a tree diagram would be the first solution. Very first position, you have 3 options, A, B, or C. In the second position, you got to get rid of the kid in the first position, and you have only 2. Notice they're a different 2 depending on which child went first. And then in the very last position, you have the only child left. There's the tree diagram visual. The fundamental counting principle would be 3 decisions in position 1, 2 in position 2, and 1 in position 3. So 3 times 2 times 1 is 6. That is fundamental counting principle. How would we do that with factorials? Because factorials will actually make this shorter, and we're about to show you that. How many different orders are possible for 10 children? Making a tree diagram is not feasible at 10 children. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That would be time consuming in your calculator. So we have a shortcut. Obviously, when the children increase in numbers, that it's even worse. So in very complex situations with high numbers, this is just not feasible. It'd take you too long to compute. So we have the shortcut, which is called factorial notation. And what the factorial key does, if you said, for example, 10 factorial, it would actually calculate 10 times 9 times 8 times 7 times 6 all the way down to 1. 10 factorial is going to be 3,628,800. If I did 30 factorial, it would give me an answer of 2.65 times 10 to the power of 32. So the factorial key is going to make all this computing very quick. And basically the algebra that you're seeing inside the red box of factorial notation is just saying n factorial, and that's whatever number you come up with, is equal to that number times that number minus 1, which is 1 less, times that number minus 2, which is 2 less, etc., all the way down to 1. So if it was 30 factorial, it would be 30 times 29 times 28, all the way down to 1. And that'll work forever. Okay? Factorial notation will always work for any number you put in. Of course, if you use a really, really high number, your calculator might not be able to handle that big of a number, and you might get an error. That's the only time you get an error, is when the numbers are way too big. So if it gets really ridiculously large, your calculator gets overwhelmed. So rewrite the solutions above in factorial notation. We kind of just did that already. So the very first one is 10 factorial. The second one is 30 factorial. There's your shortcut. A lot easier to put that in your calculator and get the answer. Okay, so senior choir has rehearsed 5 songs for an upcoming assembly. In how many different orders can the choir perform the songs? You have a couple options here. You could make a tree diagram. Take some time. It'd be a waste of time, really. The other option, you got to do the string of multiplications. So starting with 5 times 4 times 3 times 2 times 1, which is also a waste of time when you could use factorial. So just put 5 factorial and you get the answer. 6-letter arrangements from the word or the name Victor. Victor is all different letters. So all 6 letters are completely independent, no overlap, no similar, same letters. So 6 different letters. The answer is going to be 6 factorial. Express in factorial notation. Here's a little bit of practice on moving from numbers into factorial notation. So the very first one, very straightforward, 7 factorial. Basic. In B, you've got 47, 46, 45, 44, 43. So the way to deal with this question would be to turn it into 47 factorial. That would go on the numerator. But 47 factorial continues all the way down to 1. You don't want that. You need to get rid of everything after 43. So on your denominator, put 42 factorial. That way, everything after 43 is canceled out by your denominator. So numerator, 47 factorial, denominator, 42 factorial, and that will give you B. Simplify each of the following without using a calculator. So, the reverse of what we just did. What does A look like? In the numerator, you've got 6 times 5 times 4 times 3 times 2 times 1 all the way down. In the denominator, you have 3 times 2 times 1. Those 3, 2, and 1s are going to cancel out. So there's what it looks like visually, but you can cancel out 3, 2, and 1, and all you're left with is 6 times 5 times 4. So that works both ways. If we wanted to go 6 times 5 times 4 and show it as as a factorial, you go 6 factorial divided by 3 factorial, you get rid of everything beyond 4. The next one's 15 factorial divided by 12 factorial. That is going to be 15 times 14 times 13. Everything else is canceled out. (98 factorial divided by 96 factorial. You don't want to write those out. You go 98 times 97. Super simple. Saves a lot of time and space. All right, a few more here. 9 factorial divided by 3 factorial, 5 factorial. So in the numerator, you got 9 times 8 times 7 times 6 times 5, all the way down to 1. In the denominator, the easiest way to look at it is cancel out 5 factorial from the top. So cancel out 5, 4, 3, 2, and 1 directly. Now, you'll be left with 9 times 8 times 7 times 6 equals 3 times 2 times 1. But what is 3 times 2 times 1? It's 6. So cancel out the 6, and you're left with 9, 8, and 7. Now algebra, again, same idea. N times n minus 1 times n minus 2 times n minus 3, and that will go on forever until you get to 1, which you don't know what that is because you don't know what n is. It's unknown. So it's going to go on forever. However, when you cancel out n minus 2 factorial, then you're only left with n and n minus 1. Everything else is canceled out. The algebra is usually the hardest part. The more you work with it, the easier it gets. And there's a handout that's going to help you work through factorials. And there's your lesson for the day.